So the purpose of this demonstration is to give you a good visual model of how waves are propagated. Now there's two basic waves that we'll talk about, one more than another. The electromagnetic wave is a transverse wave that propagates down a pathway in one direction in the electromagnetic field. We have an electric field and a magnetic field that is perpendicular, or I should say at right angles to each other. But still the use of the spring to show the waves that we will be calculating for electromagnetic radiation at full spectrum can be done here. Before we do so, there's something called a longitudinal wave, a mechanical wave, and this is how, of course, sound propagates through air. And essentially this spring, what I'm doing, I'm going to push together the spring, and the pushing together is like pushing molecules together, like in sound, and by pushing molecules together, they're going to be pushing off on each other and propagating downward. So we'll see a mechanical wave or a longitudinal wave happen down the medium, and it should basically reflect back like an echo. So let me just try to do that here. So just push it together, and it comes back, all right? And you can actually feel that, and I'll do it one more time, a good little pulse. Again, pushing the spring together is kind of like pushing the molecules together when I speak. And then those molecules, of course, push off, and that propagates outward. So let's try that one more time with a better pulse here, all right? And you can see that pulse come back. Here we go. All right, a little more aggressive learning here. But really what I'm after today is understanding how we can understand the parts of a wave to do our calculations in terms of frequency, how often waves are made in a time period, and the length of the wave. That's a very important understanding in our electromagnetic education in terms of how electrons and photons are interrelated. So in any case, what I'm going to do here is I am going to act like a charged particle. So my hand here is a charged particle, and it's going to move in some fashion, kind of like if I was going to heat an object. So if I'm heating an object, we know that objects give off type of electromagnetic radiation, most of the time in the infrared spectrum. So just by moving a charged particle, we will create an electromagnetic field. Okay? So my hand going up and down, I'm creating a wave. Now actually I'm creating a standing wave as it's being reflected back to me, but we can still look at the components. Now, my hand's not moving much. We would say that this wave has a pretty long wavelength. Now wavelength, of course, as you can see in the middle here, there's a node, there's a spot where it's not moving. But a wavelength is basically with the start of the wave to the end of the wave. Okay, and to give you a better idea, let me see if I can make one wavelength occur. Okay, and here's a great example of one wavelength with a node in the middle. Okay, you can see that one place where it's not moving. You can see my hand going up a little bit would reflect or represent a charged particle going up and down. Now, we would say that the energy of this electromagnetic wave, it's a model, okay, is directly proportional to its frequency. Now, the frequency is how many waves are occurring, okay, in a certain time period. Now, we know the waves travel at the speed of light. Essentially, they're all going at the same speed. So if we're going to try to make more waves occur in the same time frame or at the same speed, the only way that's going to happen is my charged particle is going to have to move more often. So if I move with more energy, we can see that there's more waves here. So now, by moving faster, I think I have two full wavelengths. That gives me two nodes. Okay? So, but in order to what? Increase the number of waves occurring in a time period, okay, increasing the frequency, what happened to the size of the individual wavelength? In this case, it had to get smaller. So as the wavelengths get smaller, the frequency goes up, and as you can see, there's a lot more energy to these waves. If I move my particle even more, maybe I can make even more wavelengths, or at least increase the frequency. And I'll try it one more time as it's getting reverb back here. So I'm going to try this again. So I'm going to try to increase the number of waves between these two poles here. And again, it parallels the idea that waves travel at the same speed. So in order to have a lot more waves occur, more oscillations, I'm going to have a lot more energy in my particle to create that. So my charged particle, which could be electron, it could be a nucleus, okay, creates a magnetic field when it moves. So in order to, let's stop talking and try it. So let's see how many wavelengths I can make. But I'm going to need a lot more energy. Look at my hand. And I'm counting, maybe I have 3. Maybe. But certainly a lot more energy has to be done in order for me to create a shorter wavelength for a higher frequency. So higher the energy of my electromagnetic wave, the shorter the wavelength, and of course, the more frequent these wavelengths occur. And that's important as we look at black body radiators, molecules that are vibrating in a smaller range. If you give them a lot of energy, okay, if they're not moving, they can create tremendous amount of what? Wavelengths. Therefore, the frequency is going to be very high and the energy is very high. Molecules that move in large facets will tend to make longer waves, lower energy waves. So we talked about the ultraviolet catastrophe, okay? We're talking about the infinitesimal types of movements that all of these, let's say, atoms or these oscillators in a black body can make. And if you think about where you have to distribute in classical physics all of the energy to all of the possible modes that can be possible to infinity, we're talking about very small, little, tiny vibrations that are possible. And if you have a infinite number of possible movements to zero, then most of your energy is going to go in these little areas, and they're going to have to, because they can't move much, they're going to have to create incredible frequencies. And therefore, that's where the ultraviolet or catastrophe occurs, if in fact we have classical physics winning. Of course, it's not the case. And if in fact energy is distributed evenly to these all possible modes of vibration. Now we know, of course, atoms are quantized, and therefore their rotationals, or their ability to rotate, whether it's the nucleus or the electrons, are actually in discrete bundles, and they only have fixed energies they can have, and that, of course, will solve that. But I wanted to give you this very important visual when we talk about wavelength, talk about frequency and energy.